Okay, I think it's a good time to start. So welcome everyone to this first lecture of this morning. Will be given by Hotat Lam, who joined us remotely, and he is going to tell us about generalized symmetries in quantum field theory. Thank you very much, Hotat, for preparing and delivering this lecture. We are very much looking forward to it. Go ahead.
Thank you. Yeah, thanks. Thanks for the introductions, and also thanks for the invitation to speak at this workshop in school. I apologize that I cannot make it in person because of the visa issues. But still, I hope that with this remote lectures, people can still learn something and have some interesting takeaway. Okay, so the lecture today will be about generalized symmetries. And I understand that there has been a lot of lectures about various aspects about symmetries, anomalies, and in particular, I would like to provide a perspective about generalized symmetries from quantum field theory perspective. So a lot of things I'm going to discuss will be in the quantum field theory context. And another thing I want to emphasize is that in condensed matter, often the time when we discuss something related to symmetries, related to something that's topological, we always have in mind that we're studying some gap systems. But throughout my talk, I would like to focus on mostly gapless systems, and they are usually described by typical quantum field theories rather than topological quantum field theories. And in that case, we can see that topology still can play an interesting role, and in particular through this concept of generalized symmetries. So the plan of roughly the lectures is that I'll first give introductions about what is generalized symmetries. Then I'll discuss two kinds of generalized symmetries. One is called higher form symmetries, and the other is called non-invertible symmetries. And somewhat interestingly, both of the symmetries, both of this kind of generalized symmetries actually already appears in something that we learn in our undergrad physics, which is Maxwell theory of electromagnetism. So we can see that already by studying the simplest theories that we can ever thought of, and it's actually realistic theories, we can learn a lot about what are the kinds of symmetries that there can be, and there's a lot of lessons we can draw. So in a sense, that the lecture today is about uncovering what's Maxwell should taught us years ago, and then try to apply it more broadly. So, for example, I'm going to apply it to the case of Yang-Mills theories, which is strongly coupled to quantum field theories, and we'll see that through higher form symmetries, we can actually have some things rigorous to say about Yang-Mills theories, and we'll also study lattice gauge theories as well, using non-invertible symmetries. So this is roughly the plan of the two lectures. Okay, so before I start, let me just say a little bit about why do we care about symmetries. Okay, so this is really, So why do we care about symmetries? So here I list a few answers. So the first answer is that it's an answer would be coming from a classical mechanics persons who have learned about classical mechanics. So symmetries would imply conservation laws. And conservation laws are important, symmetries are important because first of all, they give us guidance about how to build the theories. So for example, we can build special relativity by knowing that the theory respects Lorentz symmetries, right? And then similarly, when we study systems, it's good that if we know the symmetries. If we know the symmetries, it often in the case help us to simplify the systems and help us to sometimes even solve the system exactly. So this happens, for example, in the case of hydrogen atoms, and as well as various integrable models. So one reason to study symmetries is that they provide us with conservation laws, and which allows us to understand the systems better and to build up a physical theory. And another reason why symmetry is important is that they provide us with organizing principles. So an important example that appears in the case of condensed matter physics is the Landau paradigms. So there are various phases of matters that can exist in our real world, and then even in the quantum world. And a very useful way to organize them is using symmetries by organizing them through.
Yes. Sorry, just a question. So we see the first slide. Still, is it so?
Oh, it's not moving. Can you?
Not moving. No. We see weird. Maxwell and.
Oh, is it moving now or?
Now it's moving. Yeah. But
oh, interesting.
Okay.
Got it. Okay, so I start you guys at Maxwell.
Okay, excellent.
Okay.
Yeah, thanks a lot. So now we can see it moving. Yeah.
Yeah, sorry about that. Yeah. Okay. But yeah, so yeah, I just talked about conservation laws. That one reason why we care about symmetries is they give us conservation laws that allows us to solve for systems and give us guiding principles to build the theories. And another reason why we're interested in symmetries is that it provides us with organizing principles. So in particular, through the Landau paradigms, we can organize different phases of matters according to how the symmetries are realized. In particular, according to how the symmetries are spontaneously broken. And this would actually feature a lot in Apuf's lectures. And already in the lectures that in Julian's lectures and Vijay's lectures, you might have already seen some of these examples that how we can use symmetries to organize topological phases of matters and as well as fractal phases of matters. And in Michael's lectures, you might see that this symmetries plays a role in the studies of quantum error corrections. So one reason why we want interested in symmetries is because they provide us with organizing principles. And third reasons why we are interested in symmetries is that it's not often the case using symmetries, we can deduce some results about the dynamics of the theories. So for example, in associated lectures, you might have learned about anomalies. And we'll see that symmetries, generalized symmetries can also have anomalies. And using the anomalies, we can learn a lot about various quantum field theories. And we can also learn about what are the kinds of protected edge modes that can exist in some topological phases of matters. And I believe in Zohar's lectures, we also see that using symmetries, we can use them to constrain various renormalization group flow and to constrain Lorentzian physics. So this is something that you're also going to see in these lectures. And I would like to emphasize also the use of symmetries in this perspective. And lastly, in Sanjay's lectures, you probably will see something, the use of symmetries in, for example, not just Lorentzian physics, but also about excited states, about excitations, as well as various hydrodynamics. So you can see that symmetry actually provides us with sort of overarching umbrellas that allows us to do various things. And in fact, often the case, if you want to understand the systems, we should understand the symmetry first. And once we understand the symmetry first, we can start looking for dynamics. And so the better symmetries we understand, the better we can use the power of the symmetries. So that's actually the goal of this lectures, that I would like to introduce to you symmetries that's what's called generalized symmetries. So they extend the usual notion of symmetries. And as a result, they also extend the power of symmetries in various contexts. So that's sort of the overarching goal, the reason why we're interested in generalized symmetries. Okay, so now let me say a little bit about what is the idea of generalized symmetries. And at this part, I'll be a little bit more abstract. I would like to first phrase the symmetries that we are familiar with in a slightly different language. But with this new language, it will allow us to generalize or draw analogies, allows us to generalize the notions of ordinary symmetries to various generalized symmetries. So a lot of things that I'm going to say is actually just based on very simple ideas. This idea is essentially the key insights of generalized symmetries, that symmetry and topology, they're actually closely related. Okay. And as we know that topology is something that is very robust. And as a result, that symmetry will be something that's also very robust and allows us to study various features of a systems. And I would like to demonstrate what I mean by this. So to demonstrate it, let's consider U1 symmetries in D+1 dimensions, and I'll consider it in the context of a relativistic quantum field theories. So in this case, because we have a continuous symmetries, so we have a Noether current, and this Noether current is conserved and obey the current conservation equations. And I'll discuss things in two different formalisms. One is Hamiltonian formalisms, and the other is in a Lagrangian formalisms. I'll first discuss it in Hamiltonian formalisms, which are more familiar to most people. So in Hamiltonian formalisms, what's important is that if you have a conserved current, then you can take the density of the conserved currents and integrate it over the whole space. Once you integrate over the whole space, then you obtain examples of a Noether's conserved charges. And this charge is conserved in the sense that it is an operator. I'll write an operator that acts on the Hamiltonians, that acts on the Hilbert space, by putting a hat on it. So this, if I put a hat, it means that it's an operator that acts on the Hilbert space. Okay. So when I say that charge is conserved, what I mean is that this is time independent. And the reason why this is time independent is because we can use the current conservation equations to trade the time variations of the charge density to the divergence of currents. And as a result, this will just give us 0 if we integrate over the whole space. So that means that we have, whenever we have symmetries, we have conserved charges that doesn't evolve under time. And in quantum mechanics, it means that charge operators would commute with Hamiltonians. Okay, so that means that we can simultaneously diagonalize the charge operators and the Hamiltonians, or we can label the states according to their quantum number, their symmetry quantum number. And importantly, this is conserved charges. This is not the symmetry operator that implements the symmetries. What implements the symmetry is a conserved unitary operators, which was stated in the weakness theorems. And this conserved unitary operators is essentially given by the exponentiations of this conserved charges. And these symmetry operators are labeled by some U1 phase. Okay. And yes.
It looks maybe it's frozen again. So
oh, it's frozen again.
So could you move a little bit there?
Oh, doesn't. Oh, is it?
It works, yeah, but like, yeah, I think it's fine now. Sorry.
I see. Yeah, it's probably my iPad is not responding probably smoothly with on Zoom.
I think it's all right. Yeah.
Okay, good. Yeah, I'll try to write slowly.
When you move the screen, it will be unfreeze. So I think it's okay. So thanks.
Okay, good. Yeah, thanks. And another thing about symmetry operators is that so once we have symmetry operators, the way the symmetry operator acts on the operators is that it will just transform it by conjugating the operators by the symmetry operators. Okay, and in particular, in the case of U1 symmetries, the operators can label by their charges. And so if I transform an operator or sandwich an operator by the symmetry operators, we're rid of a phase. And this phase will depend on the charges and as well as the angles of the symmetry operators. Good. And now let's try to discuss the similar things in Lagrangian formalisms. Okay. So in Lagrangian formalisms, first things to notice is that because I'm dealing with a relativistic systems, so that means that time is not a very special directions for me. I can pick time to be any directions I want. So that means that there must be a relativistic sort of uplift of what I said in the Hamiltonian formalisms. Okay. And this relativistic uplift is basically the following versions. So now you can consider the following operators, which is defined on a d-dimensional manifold, submanifold in spacetimes. Okay. And then you just integrate the Hodge dual of your conserved currents on this d-dimensional manifold. I just want to remind you that Hodge dual of a current itself is because occurrence is a 1 form, a Hodge dual is a D form because I'm in D+1 dimensions, and this is just defined by taking various contract this with the epsilon tensors. Okay, good. So we can define the following operators on arbitrary dimension D submanifolds. And one thing important to notice is that because the current conservation equations can be restated as telling us that the Hodge dual of the currents is closed. So then this actually implies that this charge that we define on arbitrary manifold is a topological operators. Okay, so this is the where I make connections between symmetries and topology. So let me explain a little bit what I mean by is a topological operators. What I mean by that is that imagine that I have an operator that is originally defined on this submanifolds, okay, M. And I want to deform these operators to make it into bigger operators that are supported on M prime. So let's look at the difference between these two operators. So the operators I start with is Qm, the operators I end up with is Qm prime, okay? But by Stokes' theorems, the difference of these two operators is given by integral of d star j on the oh yes.
It's we do not see.
Oh, it's
so when you move your screen up and down, I think it kind of gets updated. So if you kind of, but sometimes it gets frozen, and then for a while we do not. But I think whenever if you would move it up and down regularly, then it will get updated, I think. So
okay.
so
okay.
like
I'll be mindful
we
about
see
it.
it updated, and sometimes it gets frozen for a while. But after you move the screen up or down, we can see the update. So maybe you can just.
Okay, sounds good. Yeah, I'll try to. Whenever I write, I'll just move up and down.
Yeah, something like that. Thanks a lot.
Okay. Yeah, thanks. Yeah, so I hope everyone can see what I have already written. So the point is that the difference between two charges are given by the integral of d star j integrated over the regions that are enclosed by m and n prime. Okay, because d star j equals to 0, that means that these two operators are actually identical operators. Okay. Good. So this is what I mean that the operator is topological. What I mean is that I can deform this operator continuously, and by doing this, it will not change these operators. But this has an important consequence because now we can actually recover the original statements that we made before. So if I have, whenever I have a topological operators, what I can do is that I can restrict it to these operators to be at a fixed time slice. Okay. So this is what I do. So I restrict to a constant time slice. So when I restrict this operators to a constant time slice, I basically just recover this operators that I defined before, which is defined on a fixed time. Okay. But because an operator, this operator is topological, so I can move this operator up or down to a different time, right? And this will not change the operators because they're identical operators. But this is essentially a statement that this is a conserved charges. This is operator that's independent of time, right? So that's why the fact that this operator is defined on general manifolds is topological is a sort of a relativistic uplift of the statement that we have conserved neutral charges. Good. So this is the symmetry operator. This is the conserved charges. Now let's discuss how symmetry acts on operators. So before I said that whenever we want to transform our operators, we will sandwich these operators between the operator UG dagger and UG. So if I think about it in space-time language, what I mean is that I first act on the state. This is the time directions, okay? So I first act on the state, the operator UG dagger, then I act the operator O, then I act another operator UG, right? So this is how I think about this ordering of the operators in a space-time language. Good. And one thing to notice is that when I define an operators in space-time language, I should define normal directions of these operators. So for example, this operator's UG has a normal directions going up, okay? And there's one thing that's important is that UG dagger and UG are sort of related to each other by orientation reversal. So UG dagger is an operators with an arrow pointing up, but this is the same as an operators UG, but with an arrow pointing down. So they're just related to each other by orientation reversal. So in that sense, I can think about this as I have an operator. I first act on surface operators with orientation pointing down, and then the operator O, and then another surface operator with orientation pointing up. But now notice that because I'm working with the topological surfaces, right? So I can try to bring the top surface down a little bit. I try to bend it, and I also bend the bottom ones a little bit. So then eventually what we get is that we can get a sphere that is surrounding our original operator O. And this sphere always have orientation pointing outwards, okay? And this operator is essentially the exponentiations of the charge operators that we defined before. Now notice that I'm surrounding a sphere around point operators. because this sphere is topological, so I can shrink it. And when I shrink it, eventually I'll get still a local operators, right? And what is this local operators? This local operators is essentially the operators that we end up with, the O prime operators, which in this case is proportional to the original operators, but then with a non-trivial phase. So what I'm telling you is that we can think about the actions of a symmetry operators on local operators by enclosing it. Okay, so this is how a symmetry operators will act on local operators. Good. Good. Is there any question at this point about this rephrasing of symmetry operators into topological operators?
So is there any sense in which we can define this Q of M on some higher genus manifold?
Higher genus, yeah, you can definitely do that. There's no problems. You can define it on higher genus manifolds or whatever manifolds you want, as long as its dimension is D.
So what would be the physical meaning of defining it on a higher genus manifold?
Oh, that's a good question. So if you're thinking quantum field theory is nothing but some kind of defects in space-time, but it doesn't necessarily have a good Hilbert space interpretations. Maybe, but it's a well-defined operator in space-time. You can insert it in path integral. You can compute expectation values.
Okay, thanks.
Yeah, good. Thanks for questions.
Quick question.
Oh yes. Mm-hmm.
Well, first, the left-hand side of your screen is cut off. We kind of see black. It's not fully showing.
Oh, okay.
Yes, now we see it.
Sorry, sorry about that.
It's okay. And now, quick question. When you show the, let's see, on the right-hand side where you talk about the Lagrangian formulation, there's a line where you compare the difference between charges on the two manifolds, M and M prime. Right?
Mm-hmm.
So the right-hand side gives you, yeah, exactly. So the right-hand side of the equation, what is the integration over? What is N? Is that some boundary between M and M prime?
Oh yeah, so N is the volume enclosed by M and M prime. So N would, yeah. So let me just write an equations. So N has a property that its boundary is given by M minus M prime.
Right. Exactly.
Yes.
I see. Okay. And so I'm just trying to see how you're presumably using Stokes' theorem, right, to do that? Because Q of M is just integral over volume. Oh, but when you subtract, you get the difference, which is the boundary. Okay. Thank you.
Exactly. That's right. I'm using the Stokes terms. Yeah. Any more questions? Good. Okay. So I'll just proceed. Okay. Good. So now,
can you hear me? I have a question. Can you just go one slide above? Sorry.
Yeah. Oh yeah, please. Yes.
In the last line, there is this two surface. The top surface is UG and the bottom surface is UG dagger. And when you sandwich them, why this this sphere is just UG? Like, where is the information of the orientation change, etc.? The dagger. I did not understand.
That's a good question. So let me explain this again. So strictly speaking, when I talk about UG dagger, I already fixed the orientation to be up, okay? But then this is just UG dagger. I want to make it into UG. So if I want to make it into UG, then I'll do it by changing the orientation down. So in other words, UG as an operator in spacetimes is related to UG dagger with opposite orientations. Does it make sense? So once I replace it by UGs, then it's clear that it becomes a single operators. Good. I'll proceed then if there's no more questions. Good. So okay. So I gave you a way to rephrase this symmetry operators in terms of. Oh, sorry. There was a question. Oh, yes, please.
Can we go back to the as far as the support of UG and UG dagger are concerned, meaning if I think of O as an operator acting on some degrees of freedom, does UG and UG dagger exactly act on the same degrees of freedom? And All of them, and what does it mean to that they share a boundary? When you say it deforms and they share a boundary, what does that mean?
Oh, I see. What I mean was pretty simple. Let me see. So I start with a configuration like this, right? So I have a UG and UG. Let me let's call them UG, but then I have opposite orientations, okay? Then I can deform it, and when I deform it, I can make it into something like this, right? Something like this. My bad drawing. Roughly speaking, some operator like this. So I'll pinch off the boundary first, but then when UG and UG dagger meet away from the operators, they will just cancel each other. They will just become identities. So then you just get something like this, like a sphere. Does it make sense?
Thanks.
Yeah. Good. I'll present something about the fusions that will probably make this point even clearer. Okay, so I've been telling you how to think about U1 symmetries in terms of some topological operators in space-time. So now let me try to state the general result, a general way we think about G symmetries. Okay, so a G symmetry is here. G is a group which can be non-abelians. It doesn't need to be U1s. So the way we think about a G symmetry is that it has first it is defined by a set of topological operators in spacetime, or so we can insert that in path integral. And these operators are defined on importantly a codimension one manifold. Okay. And these operators are also labeled by group elements in this group G. Okay.
That can you
I
just
think
move the
it's
screen?
froze again.
Yeah.
Yeah. I tried to move it. It doesn't quite work.
Yeah.
Let me see. Okay, yeah, it suddenly appears. Good. And now I have a bunch of operators which are defined on codimension one manifolds, and they are labeled by group elements. So then because they are topologicals, then we can imagine doing the following things. So imagine that we have two parallel operators, which are like this, right? So we can deform it so that we make the upper part, upper half of these operators to be very, very close to each other's. And eventually we will just fuse them. We just put them on top of each other's. But meanwhile, we keep the bottom parts to be away from each other's. So then eventually what we get is something like this, which forms some kind of junctions, okay? So at the bottoms, so the two operators that we start with, one is labeled by G, the other is labeled by G prime. And when we bring them together, we will get another operators, and this operators is given by, it's labeled by G times G prime. And G times G prime is essentially how group multiplication works in this group G, okay? So this is what we mean by UG times UG prime. Good. And importantly, the junctions that they meet.
Quick question. So I didn't quite get the ordering of this. So you have these two manifolds. So how do you think about the ordering of these G prime versus G prime G?
Oh, that's a very good question. So here because I'm working in a relativist quantum filter, so I don't pick a preferred time directions. But if you want to pick a preferred time directions, we can, for example, pick this direction to be preferred time directions. Then this means that I will first act UG first, then I act UG prime. Okay, so in that case, then what I wrote is not quite correct. G prime and G. Remember that this operator has a preferred orientation. So let me first pick orientation to be this way. So yeah.
Okay, thanks.
So the ordering is essentially fixed by the orientations. Yeah. Good. So what I'm saying now is that we have a bunch of topological operators which are labeled by group elements that are defined on codimension one manifolds, And we can read off the informations of this group by fusing them. So essentially, the group determines the fusion rules of these operators. Okay, so these operators, they will obey a group multiplications fusion rules, and this is essentially determined by the symmetry group. Okay, so first of all, the reason why I want to rephrase this operators in this language is because it is good for several things. So the first thing it is good for is that it is good for discrete symmetries. So for discrete symmetries, we don't have another current, but we can still define these operators, and these operators are just labeled by group elements. So for example, Z2 symmetries means that your theory has two operators, the identity operators and the non-trivial operators. And if I fuse this non-trivial operators with itself, then it gives you the identity operators. So it's just obey a Z2 fusions. The second reason why I want to phrase it the symmetry in this way is that, you see, so far I actually make no full reference about the Lagrangians or Hamiltonians, right? That I don't need to say, oh, I have a Lagrangians, and then I do a specific symmetry transformation on some fields, and then the Lagrangians is invariant. I don't need that. All I need is that I just need this invariant notions of topological operators. As long as your theory has this topological operators, it doesn't depend on which Lagrangians that you use. And often the case, a theory could have multiple Lagrangian descriptions. So we can see the way to phrase symmetries using these topological operators is that it allows you to phrase symmetries in a Lagrangian invariant way. And for express, it also means that I want to phrase it in a way that's invariant under the duality frames. Okay, so this is a Lagrangian independent definitions. Good. So and another thing is that I didn't discuss how symmetry acts, right? So we can just do the same things as before. So now imagine that we have our symmetry operators, which are defined on some surface, and then we also have some operators we want the symmetry to act on that. So one way to act the symmetry operators on that is that we can bring the symmetry operator past the local operators. Okay, so when we bring it past, we will create these little bubbles, right? And then I can eventually bring it past and then pinch off the bubbles. Then what I get is that I bring the operator past, but then I have this spheres surrounding the operators that we have. And then we can shrink this spheres, and then this will implement the symmetry transformations. So essentially, the symmetry transformations could be implemented by moving a symmetry operator past some local operators. And this is how the symmetry transformations will implement by the symmetry operators. Okay, so the reason why I go through all this is that it's not just that I want to rephrase symmetries in some topological operator language. It's because I want to use it as a basis to generalize symmetries. So this is what I mean by so we'll see that with this way of thinking about symmetry operators as topological operators, it's very easy to generalize the symmetry, the notion of symmetries to various forms. So for example, we are going to discuss higher form symmetries in the lectures. So what higher form symmetry does is that it keeps this and this to be invariant, but then it changed these assumptions. So what it does is that it says that instead of consider codimension 1 operators, let's make the operators to be higher codimensions. Okay. So this leads to what's called higher form symmetries. So in particular, in 2+1 dimensions, ordinary symmetries would be implemented by a surface, which is codimension 1. But then there could be higher form symmetries, which are implemented by some loops, okay, which are codimension 2. So topological operators in 2+1 dimensions, also topological line operators in 2+1 dimensions will implement higher form symmetries instead of ordinary symmetries. So this is the first generalization we encounter. The second generalization we encounter is what's called non-invertible symmetries. So what is non-invertible symmetry? So non-invertible symmetries, it's a symmetries that generalizes that fix these conditions and these conditions, but then change these conditions. So non-invertible symmetries change how the symmetry operators will fuse. So the symmetry operators will not fuse according to some group multiplications. It will have some more general fusions. So in particular, I'm going to explain later that it replaced a group-like fusions by what's called a non-invertible fusions. Okay. So in fact, this non-invertible fusions, some of these non-invertible fusions you might have already seen in Julian's lectures, I believe. So what happens is that if you take an operators and then you try to fuse it with another operators, usually in the case of group-like case, you just get a single operators coming out. So you just get operator UC. But in a more general case, you can get not just one operators, you can get more than one operators, you can get multiple operators, right? And this is essentially what's called non-invertible fusion, is that if you fuse two operators, you get more than one operators, you can get multiple operators. Okay, so this is what I mean by non-invertible fusions. Yes, please.
Yeah, so you argued that this G was a topological operator using this Noether conserved kind. How do are you just now taking this as an axiom for discrete groups as well, or is there an argument to show that this will be also true for discrete groups?
Oh, good. Yeah, so this is also true for discrete group. The reason is very simple. So, operators, right? Sorry, a symmetry operators is conserving time. So that means that it is invariant if I move it up in time. Okay, but then because using locality together with relativities, then you can argue that this operator should be topological operators defined on general manifolds. Because relativity tells you that time is not a special directions. You can pick it to be other directions, and then so that's why even a discrete symmetries would be described by this topological operators. Just coming from the fact that you have conserved symmetry operators for discrete symmetries together with locality and relativity.
Okay, thanks.
Yeah, good. Are there any more questions before I move on to discuss details of higher form symmetries? Good. So I guess there's no more questions. Good. I'll now discuss higher form symmetries. I'll still say something a little bit high level, and then we'll quickly go into examples. Okay. So at this stage is still something that might be a little bit abstract or high levels, but then we'll quickly see examples. Okay. So I just copy and paste the various properties zero form symmetries should obey. But now let's discuss how to generalize this to higher form symmetries. So in particular, we can label the form degrees of higher form symmetries by Q. So I'll consider what's called Q form symmetries. So a Q form symmetries, again, are labeled by some topological operators, UGM, and this G are taking values in the symmetry group G. But now we are not considering a codimension 1 operators. We are considering a codimension Q plus 1 operators. Okay. So in particular, the ordinary symmetries will be what's called zero form symmetries, because that if we specialize Q to be 0, then this exactly recovers the ordinary case. So now if I have a codimension Q plus 1 topological operators, then one thing to notice is that these operators will not act on a local operator anymore. It will instead act on Q-dimensional operators. Okay. So let's do an examples. So in 2 plus 1 dimensions, we can consider one form symmetries. So one form symmetry is generated by codimension 2 operators. And codimension 2 in 2 plus 1 means that we're considering some lines. Okay. Okay. So let's say we have these lines, and then we also have some local operators. We want to apply these lines to the local operators. But there's no way we can do it because this is a topological operators. So we can just move it past the local operators and shrink it and make it disappear, right? So that means that the operators, the line operators cannot act on local operators. But now suppose that we have our symmetry operators, UG, surrounding or link with another line operators in 2+1 dimensions, which I got W, then there's no way we can make this. There's no way we can make this UG operator disappear without shrinking on this W, right? So that means that if I shrink this UGs, it will apply a symmetry transformations on this W. And this symmetry transformation can at most be a phase, okay? So this is how one-form symmetries in 2+1 dimensions acts on some line operators. And good. So the fact that this codimension Q+1 operators acts on codimension Q operators just simply follows from the fact that a codimension Q+1 operators can link with codimension Q operators, and that's it. Link with the Q dimension operators, and that's it. Good. So now there's another consequence of this higher codimensionality is the following. So when Q is greater than 1, one can show that the symmetry operators has to be commutative. So the reason is very simple. So let's imagine that this is the time directions, okay? So we can first act an operator UG and act an operator UG prime. So this gives us an operator UG prime G. But notice that this operator is topological. So what I could have done is that I could shrink it and bring it past here, right? Without acting on the other operators, I can just shrink it and make it pop up again. So that means that there's a smooth configurations, smooth things we can do that exchange smooth continuous actions we can do that exchange UG and UG prime. And as a result, we get, and then we can fuse them again, and as a result, we get a different operator, UG G prime. So that means that this group actually has to be commutative. So the group has to be abelian. So the symmetry group for higher form symmetry has to be abelian. So this is a very strong constraint on the possible higher form symmetries that one can consider. Okay. Good. So let me just summarize what I have discussed. So by simply generalizing topological operators from codimension 1 to higher codimensions, we learn two facts. One is that this higher codimension operators will act on higher dimensional operators instead of local operators. Second is that this topological operators, they has to be commutative. So the corresponding group has to be abelian. So we can see that already from this very simple assumptions, we can derive something pretty profound.
So Bhattacharjee, can I just ask a question?
Please.
Yeah, so I'm just wondering, do you need this group to be abelian, or do you need it to have an abelian representation?
The group is abelian. The group is abelian. So I mean, a trivial representation is always abelian representations, right? So every group has a abelian representation in that sense.
Okay. Okay.
Yeah, we need this group to be abelian. Good. Is there any more questions? Okay, that's good. So now I'm getting to the sort of the real examples now. So I hope everyone's still with me, and then now we can start discussing some concrete examples and to bring all the abstract things that I talk about into real life. Okay, so the example I'm going to consider is nothing but Maxwell's theory of electromagnetisms. So in other words, I'm considering what's called U1 gauge theories. So this is the actions of the theories. It's given by just, I also use a differential form, so it's given by F wedge star F. And this F is the field strength, and A is the gauge fields or the gauge connections, okay? So the field strength is given by dA, and then this gauge connections has a gauge symmetries, which is amounts to shifting A or identify A up to d alpha, and where alpha is a scalar. But one thing important I want to emphasize is that I'm considering a U1 gauge theories. So that means that the scalars, this gauge parameters has a 2-pi periodicity. It's actually a periodic scalars, okay? And I'll always normalize it to be 2-pi periodic. And this will actually have far-reaching consequences, as I'm going to mention later. Okay, so what are the symmetries in these theories? So the claim is that the theory has what's called electric U1 one-form symmetry. So what is the corresponding currents? It's a continuous symmetry, so it has a current. So the current is a two-form current. So remember that a current for a usual ordinary symmetries is one form, but in the case of a one-form symmetry, it's actually two-form. So the form degrees goes up. So in that sense, it's higher form. And this current is given by I over E squared F, okay? And one can check that these currents obey the current conservation equations, which is nothing but D star F right by E squared equals to 0, okay? So the reason why you get this equation is just coming from the equations of motions of A. So if you, so this is nothing but the Maxwell equations essentially. Yeah, this is one of the Maxwell equations. Good. So we have this electric one-form symmetries, and it has corresponding the two-form conserved currents. And you can ask, how should I think about this symmetries? How does this symmetry act on the field? The way this symmetry acts on the field is by shifting the gauge connections by a flat connections. Okay, so lambda mu here is a flat connections. So if I shift A by flat connections, then I'm not changing my field strength, right? So my field strength will be invariant under this symmetry transformations. So as a result, my Lagrangian is invariant. Okay, so this is what generates the one-form symmetries. It's just shifting the gauge connections by flat connections. Okay, so now let's discuss what are the operators charged under the symmetries. So because this symmetries are shifting the gauge connections by flat connections, so a very natural thing is that we charge under this symmetry is what's called the Wilson lines. Okay, so Wilson line of charge Q is given by the exponentiations of the holonomy of the gauge fields A. So this is Wilson lines. And how do we think about Wilson lines? So the way we think about Wilson lines is that we can think about Wilson line as some kind of rule line of some probe electric particles. Okay, so it's a probe. You can think of it as some probe electric particles in your theories. And one thing that's important is that because we are working with the U1 gauge theories, so the charge turns out to be quantized, they're integerally quantized. So this is what we have seen in our real world, right? That the charge is actually quantized. That there's a fundamental units of charge, like electrons has the smallest electric charge. So all the charge are quantized. So this is a feature of a U1 gauge theories. Okay, so we have Wilson lines, and since Wilson lines are exponentiations of A, so we see that under the symmetry transformations, this Wilson lines will acquire a non-trivial phase, which is given by the integral of lambda, right? So this is how a Wilson line will transforms under the symmetry transformations. So Wilson lines is the operator that are charged under the one-form symmetries. So, and remember that before I described how a symmetry, a zero-form symmetry acts on local operators, now we can describe how a one-form symmetry acts on these Wilson lines. So the way we could implement this is that we can surround these Wilson lines by our surface operators, which implements the symmetries, which is given by exponentiations of I alpha of star current. Okay, so this is an operator that are defined on some surface. Remember that I'm considering a one-form symmetries, so we should consider a coordination two operators. So that's why it's a surface operators, and a surface operators in 3+1 dimension can actually link with the lines. Okay, so now if I shrink the surface operators on the line, I make it disappears, and then as a result, we'll generate a phase, and the phase is essentially the charge of the Wilson lines. Okay, So this is how a symmetry operators acts on the electric one-form symmetry operator acts on the Wilson lines. But if you look at this, this is actually nothing but the statements of Gauss law. So this operators that we're talking about is actually essentially the integral of the electric flux. And so we know that Gauss law is something that's topological, right? That you just pick any surface that encloses your probe charge, then you can just read off the charge of the probe charge. So that's essentially what the one-form symmetry is doing. It's just reading off the probe charge. And this probe charge is represented by the Wilson lines. Okay, so the theory has an electric U1 one-form symmetries. But more interestingly, the theory actually has another one-form symmetries, what's called the magnetic U1 one-form symmetries. And this symmetry is somewhat unconventional from a usual perspective. And let me say a little bit more what I mean by that. So first of all, what is the current for this symmetries? The current for this symmetries is given by 1 over 2 pi star f. Okay, so this is again a two form in 4 dimensions. So this current is again closed. The reason why this current is closed is because if we look at the equations, it's telling you that we're essentially getting something that is proportional to exterior derivative of f. And exterior derivative of f is nothing but d squared a, right? And this equals to 0 just because of the Bianchi identity. So you see, this is something a little bit weird if you're coming from a usual way we think about symmetries, because this current is always conserved. It's actually conserved, has nothing to do with Lagrangians or nothing to do with what Lagrangian wrote down. It's always a conserved current. It's very different from electrical one-form symmetry. Electrical one-form symmetry is conserved only because of the equation of motions. And that means that it's conserved only for this very specific theories, right? That because equation of motions are derived from the actions. But this magnetic one-form symmetries is just always conserved because of the Bianchi identities.
So what you just said, that last statement, so that's true if you don't have any magnetic monopoles, right? But if you imagine that you have a theory that has both electric and magnetic charges, right? Then magnetic one-form symmetry would not be conserved?
That's correct. That's correct. Yeah. So far, all my statements is just in the free Maxwell theories that doesn't have any dynamical charge coupled to it. So in this theories, then there are Wilson lines, and there are also what I'm going to mention. There is also a TOF lines, and they are what charge on the symmetries. But now, once you have dynamical monopoles and dynamical electric charge, all the symmetries are broken. Okay.
Gotcha.
But then, please.
And if I may, one other question is about the interlinking. So in the picture on the left, when you talked about the Gauss law, you had a one form, you had a Wilson line, right, which is defined on a one form object. And then you kind of drew a sphere suggesting that that's your two form that's defined on that sphere. Is that what you're doing there?
That's right. Yeah, because I cannot draw things in 3+1 dimensions. Yeah. So yeah, if you want, I'm actually mixing dimensions here. So if you want, I can represent my Wilson lines as just a point here, but it's a point in a constant space-time. So you can think of I'm drawing it in 3 dimensions, and then there's a Wilson line extending in time directions. Yeah, to make it more precise.
Okay.
Yeah.
Thanks.
Good. Yeah. Thanks for the questions. Are there any more questions or? Good. Let me complete this and then I'll stop for more questions later. Okay. So one thing I want to emphasize is that that's very confusing, but then you should take it as a feature, not a bug, is that the symmetry actually does not act on the gauge fields A mu. So this is a symmetry that doesn't have actions on a fundamental field. But this is not a problem at all, because this also highlights sort of the the good way, the good things about thinking about symmetries this way is that we think about symmetries as topological operators. We don't think about it as the actions on the fundamental field. And in fact, as I'm going to mention later, that this U1 gauge theory actually has a duality. So you can apply electromagnetic dualities, and then you will get what's called a dual gauge fields. And this magnetic one-form symmetry is, in that case, actually acts on the dual gauge fields. So you see that whether a symmetry acts on fundamental fields or not actually depends on which duality frames you pick. Okay, but this is just a flawness of thinking about symmetries in terms of the actions on fundamental fields. We should think about symmetry in this more invariant way. Okay, so now it doesn't act on the fundamental fields, so there's no way it can act on Wilson lines. So what are the objects it acts on? It acts on what I mentioned before. So I'll again draw as a line extending in time directions, but it's look like a point in space. So this is what's called the Atoff lines. Okay.
Sorry, can I ask a question before that?
Yes. Let me complete the writing. Yes. Please go ahead.
So there's another way in which very disconcertingly the electric and magnetic high form symmetries are different. On the electric two form symmetry, it seems like you need to impose the equations of motion. Whereas
exactly, that's right.
Magnetic, it does not. And somehow it's a bit disconcerting to say that symmetries are only applicable on shell. So could you comment?
Oh. Yeah, I understand what you're saying. Yeah, so this is never a problem because everything you compute actually on shell, like because you're computing correlation functions, right? I'm saying that when I insert these operators in correlation functions, it's topological. So that's why you can always use things on shell. You can always use the equation of motions you want. This is not a problem. Because essentially everything is on shell. There's nothing off shell. Like all observables are you compute you have to go through the whole path integrals.
I'll think about it.
Mm-hmm. Yeah, this is a confusing point. Yeah. Yeah. But yeah. Yeah, I can explain more later if maybe after the lectures. Okay. So good. So we have this magnetic one-form symmetries. It doesn't act on Wilson lines, but then it acts on Atoff lines. And Atoff lines, the way we think about Atoff lines is that it is essentially the roll line of a probe magnetic monopole. Okay, and the way to define a Atoff line is very unusual in the this duality frames. If we define it in a different duality frames where you have this dual gauge fields, then it's essentially the Wilson lines of the dual gauge field. So it's very easy to write down it in different duality frames. But in this duality frames, the way we define it is that we should think about Wilson lines as some kind of boundary conditions. So we have the Wilson lines. Well, the way we define it is that we carve out sort of a tubular neighborhoods around this Atoff lines. Okay. And then, so on every cross sections, there are some spheres, right? And then we impose the condition, the boundary conditions on that spheres by saying that the total magnetic flux around that has to be non-trivial. And because I'm working with the U1 gauge fields, the flux is quantized. So we require that the flux coming out from that is non-trivial and it's given by some 2 pi times integers. Okay. And that integer determines the charge of the Atoff lines. So you see that if I define Atoff lines in this way, then by definitions, Atoff lines is charged under the magnetic symmetries, right? Because if I surround this Atoff lines by my one-form symmetry operators, which is given by nothing but the exponentiations of the flux, the magnetic flux, then because this is again something like a Gauss law, so monopoles will just emit some non-trivial magnetic flux, and this is exactly what this magnetic one-form symmetry is measuring. So that's why, by definition, the Atoff line is charged under the magnetic one-form symmetries. Okay. Good. And so if we shrink it, then what we get is that we'll again get a phase, and this phase is proportional to the charge of the Atoff lines, or the total flux of the Atoff lines. So this the statement that we have a magnetic one-form symmetry is nothing but flux conservations. Okay, and but this operator is just measuring magnetic flux. Okay, good. Is there any questions at this point? I want to mention that I'm going to say a little bit more about electromagnetic dualities later when I'm talking about non-invertible symmetries. Good. So if there's no questions, then I'm going to move on to the sort of the real meat of higher form symmetries. So far, I've gave you the definition of higher form symmetries. I gave you some abstract formalisms and gave you some examples. But then you can ask, why do we care about higher form symmetries? So the reason why we care about there's the questions.
So I mean, you didn't go into much details about electromagnetic duality, but so this EM duality only holds in on-shell condition because there is a
no. So electromagnetic duality is the exact dualities between two full quantum theories.
Right.
Yeah, I'm going to explain later. Yeah, it's actually pretty subtle, the dualities.
Thanks.
Yes. Yep. Thanks. Yeah. Good. Okay. So now I'm going to discuss why we care about one-form symmetries. The reason why I care about one-form symmetry is that once we have this giant notion of symmetries, then we can discuss we can organize spaces of matters according to whether the symmetry is spontaneously broken or not. Okay. So let me first quickly review how we think about zero form symmetry when it's spontaneously broken. So the way we determine whether a zero form symmetry is spontaneously broken or not is that we can look for order parameters, right? And then we ask whether the order parameters has non-zero expectation values in the vacuums or not. If it has non-zero expectation values, then that means that the symmetry is spontaneously broken. And the way we can measure whether, or we can determine whether order parameters develop non-zero expectation values or not is by looking at two-point correlation functions. So let's say we take two operators, an order parameters and its charge conjugations. Okay, we can look at their correlation functions. This correlation function has non-zero expectation values. And then we can ask what happens if we take these two operators to be very, very far. So when we take these two operators to be very, very far, the first things to notice is that by cluster decompositions, this correlation functions becomes the same as the expectation values, the square of the expectation values of the operator phi. Okay, so this use the clustering properties. So that means that we can read off whether the order parameter has non-zero expectation values or not by looking at what happens to this two-point correlation functions at long distance. So if I take this distance to be very large, then there are two possibilities. One possibility is that it approaches some constants, okay? So it just approaches some constants. So that means that this order parameters has non-zero expectation values in the vacuums. So the theory goes through spontaneous symmetry breakings. Another possibility is that this correlation functions can decay with distance. So this just means that the system is preserved, the symmetry is preserved. And this decaying is like there's some charged particles, some particles charged on the symmetries that propagate between these two local operators. Okay, so this is a way to diagonalize whether diagnose whether a symmetry is spontaneously broken or not by looking at whether two-point functions has long-range correlation functions or not. And there's a okay, that's right. Okay, so now let's discuss what happens to one-form symmetries. Okay, so suppose we have a one-form symmetries that are spontaneously broken. So this is a generalizations of the Landau paradigms in the sense that we can now use one-form symmetries, whether it's spontaneously broken or not, to characterize phases. So I'll refer to it as some higher form Landau paradigms. Okay, and I believe Approve is going to discuss more generalization of Landau paradigms in his talk. So now, let's try to mimic what we did in the zero-form symmetries. So in the case of zero-form symmetries, we look at two order parameters, and then we look at their correlation functions. So in the case of one-form symmetries, what's charged under the symmetries is some loop operators, right? Some line operators. So what we can do is that we can now take our line operators, which are supported on some curve, and we ask what happens if we make this curve to be large. Okay, we want to consider a case where this curve is large. Then when we take this curve to be large, then there are again two possibilities. So one possibility is actually let me get this bigger. One possibility is that we can have parameter law. So roughly speaking, that means that the correlation functions scales roughly as how big the curve is, scale as the perimeter of the curve. Okay, and another possibility is that it can decay with the area enclosed by this curve. Okay, so this is what's called the area law. So I want to, if we want to draw analogies, then I want to say that perimeter law means that the symmetry is spontaneously broken. And then the area loss means that this correlation function decays much faster. So then this means that the symmetry is preserved. Okay. So this is to just to draw analogies with a zero form symmetry case, and I'm going to motivate what I mean to why this is a correct criteria.
For that, I have a question.
Yes.
I remember that even with higher form symmetry, you can also have zero law rather than the perimeter law. You can have zero law, perimeter law, and area law. Depend on the physical system.
That's right. That's right. I'm getting to that. Just give me a few minutes, then I'm getting to that. Yeah, okay. If that's okay. Okay. So let's discuss what is sort of the physical meanings of this perimeter law, area law, or even a zero law. Okay. Let me just say zero law just means that the operator expectation values doesn't depend on the length at all. It can happen, for example, as the topological operators. Okay, so the physical meaning is the following. So let's think about discharge operators is essentially the Wilson lines in our stories. Okay, so then if we have a Wilson lines, I can consider a Wilson lines that are supporting on a sort of a boundary of a rectangle. So I have this direction as time, and this direction as a separation of two length. Okay, sorry, go ahead. Yeah. Is there a question?
Hello, I am. Just to kindly give a reference of it.
So someone is asking for reference for, is that right?
Yeah. For this perimeter law and the area law in this context, spontaneous symmetry breaking context.
When you say reference, you mean like a literature reference, or you mean like examples?
Exact.
Oh, you mean examples? Okay. Oh yeah. So yeah, I'm getting to that. So actually, give me a second. Let me discuss the implications of this perimeter loss and area loss. Then I'll discuss examples. Yeah. But just quickly to say that an example of perimeter law is that what happens in the case of Maxwell theory. You have perimeter law. So that means that one-form symmetry, the electric one-form symmetry we talk about, are spontaneously broken in Maxwell theories, and it has non-trivial consequences. And for the case of area law, that happens in confining theories, and that happens, for example, in Yang-Mills theories. And I'm going to discuss examples soon. Okay, so let me discuss. I already mentioned the words confinement. So the reason why one-form symmetry, spontaneous breaking of one-form symmetry is important is because it's tied with confinement and deconfinement. So let's take the example of a Wilson lines, and then we try to compute the expectation values of a Wilson lines on rectangle. Okay, and so if I compute the expectation value of a Wilson lines on rectangle, I can think of it as the following. So because I take this to be a time directions, so I can think of it as and I take this direction to be very, very long compared to their separations. Okay, So then what this Wilson line, the expectational value of this Wilson loop is measuring it is measuring the potentials between two probe particles. So the expectation values of this Wilson loop is nothing but the potentials between these two probe particles represented by the Wilson lines and times the time directions. Okay, so remember that I'm taking time to be much, much bigger compared to their separations. So now, when I say the Wilson lines have perimeter law versus area law, what I mean is that whether these Wilson lines behave as proportional to some constants times time directions, because time is much bigger, or some or r times t. Okay, some constant times r times t. So that's what I mean by perimeter law versus area law. But then you see, the perimeter law means that my potential actually approach a constant at long distance, right? So perimeter law means that I have a deconfined potentials, that it takes finite energy for you to bring the particles apart, that the potential only get to constants at long distance. So that's why it means deconfinement. But in the case of area law, that means that the potential is proportional to the separations, right? And in that case, it will take infinite energy to separate two particles. That the energies to the more you separate two particles, the more energy you pay. So that's why it corresponds to confinement. Okay. And let me also mention one thing. It's related to the question that we ask. So remember that whenever we think about potentials, we can always shift up potentials by some constants, right? It doesn't matter, because the most important thing for us is the difference between two potentials at different the difference between potential at two different points. So if I shift the reference points, or shift the reference potentials for my physical potentials, then what it does is that it's just redefining my Wilson loop operators by a term that is proportional to the volume, to the reference, to the reference potentials that I shift by, times the length of the currents. So what does it mean? It means.
Sorry, can you move the screen again, because
sorry.
I cannot see you.
Sorry. Yeah, there's a delay. Oh yeah, perfect, it's coming up. Okay, so let me just state what I said before. So if you shift the reference point of the potentials, what it does is that it's shifting the operators by a terms that is proportional to its length. Okay, so this shift is essentially a shift. It's essentially a redefinition of the operator by what's called counter terms, a local counter terms supported on the operators. So now this comes back to the question that we ask. So if I have an operator that obey a perimeter law, then what I can do is that I can pick some preferred reference, preferred counter terms, so that my operator actually doesn't decay as we make it bigger. We can make it into what's called a zero law, that this is an operator whose expectation value doesn't decay. Okay, so in that sense, zero law and perimeter laws are essentially the same things. They are just related by redefinitions by counter terms. On the other hand, area law, if you have area law, there's no way you can fix it, right? If you shift something that's proportional to the perimeters, there's no way you can make an area law into something that's finite. So that's why that's why what I said is very close to, in parallel to zero form symmetry breaking, because in the case of perimeter law, you can always redefine it to make it into some non-trivial something that doesn't decay with the distance. But for the case of area law, it always decays with distance. So that's why it's in analogies with zero form symmetry, spontaneous zero form symmetry breaking.
I have a question about that.
Please.
So in your zero form case, you have a local order parameter, right? And then you can either say that it's like non-zero in the SSB phase or vanishing, or you can diagnose it with a correlation function of right? So of two. So here in the one form case, I just wondering, so this W, so this is the, it plays a role of the order parameter itself, right? So,
that's
so then my question is like this analogy when you make it large loop or small, I do not see complete correspondence to the, because then it sounds that on the, if you would want to think about analogy of the correlation function on the left-hand side, you should think actually about correlation function of Wilson loops, right? Or
good. That's a very good question. So let me clarify. So this, if this curve is contractible, then this is actually in parallel to this. Okay, so if it's a contractible, it's this thing is parallel to this. But if this curve is non-contractible, so let me do an example. So say if our spacetime has some non-trivial S1, okay, so for example, if I'm studying a thermal systems, then my time direction is compactified. Then I can have Wilson lines wrap around the time directions. So this Wilson lines that wrap around time directions, if the symmetry is not spontaneously broken, should have zero expectation values using a selection rules from the one-form symmetries. But it can have non-zero expectation values, and in that case, it means that the one-form symmetry is spontaneously broken. So this non-contractible loops is sort of the analogies of this order parameters. And these things, there's no reason, there's no selection rules that forbid a contractible loop to have non-zero expectation values. So that's why this is more closer to this. So to make the analogy even stronger, so you see, if I say this corresponds to a single y, then now if I have another operators wrapping around it, then this is like considering a two-point function of phi and phi prime. And this things is now a contractible loops, right? So that's why this is that's why it's closer to these things. So the option is this is contractible loops and this is non-contractible loops.
Okay, I think this helps a lot. Yeah. Thank you.
Good. Oh, and just to mention the name that so in the study of gauge theories, a loop that wrap around the time directions in a thermal systems is what's called Polyakov loop. So this is the order parameters that diagonalize confinements and deconfinements. Okay, so again, I start with something that is high level, but now we want to see these things in actions. Okay, so what I mean is that remember that in the case of zero form symmetry, if you have a continuous symmetry that is spontaneously broken, then you have massless Gaussian boson. And in this case, in the case of Maxwell theory, your potential, if you look at the potential, it decays with distance, right? It's a Coulomb potential. So apparently it will goes to zero. So it goes to finite numbers. So that means that we're in a deconfined phase. Okay. And so that means that the one-form symmetry is spontaneously broken. The electric one-form symmetry is spontaneously broken. The electric one-form symmetry is spontaneously broken. So that means that because it's a continuous symmetry that's spontaneously broken, so it means that there should be a Gaussian bosons. And what is this Gaussian bosons? This Gaussian bosons is nothing but photons. So photon should be thought of as the Gaussian bosons for the one-form symmetries.
It's frozen again.
Okay.
That is frozen again.
Let me move it again. Okay, it's not coming up. Oh, good. Yeah, that's responding now. Yeah. So let me just restate what I said. In Maxwell theories, we have a deconfined potentials. So Wilson lines obeys perimeter laws. So in fact, even a TOF lines obeys perimeter laws. So that means that both the electric one-form symmetry and magnetic one-form symmetry are spontaneously broken. But since they are continuous symmetries, so if they are spontaneously broken, then that means that there must be some Gaussian bosons. And the Gaussian boson in this case is nothing but photons. So in fact, there essential clues that why photons should be thinking about as Gaussian boson, right? Because symmetries acts on phi as a shift instead of transformed by some phase. Okay, so that means that symmetry is realized non-linearly on the field. So that's why photons is the Gaussian bosons. And another reason, another way to see this is that we can now act our currents on the vacuums, and this will have non-zero expectation values with the photon states, which is proportional to, roughly speaking, epsilon mu nu p nu minus p mu epsilon mu. Sorry, nu. Okay. So the statement is I want to get to is that one-form symmetry can be spontaneously broken, and if spontaneously broken, then there are consequences. And in this case, because it's a one-form symmetry, U1 one-form symmetries, so if spontaneously broken will lead to photons, which is a Gaussian bosons. Good. Is there any questions about this? Okay, if not, then I would like to discuss one very important aspect about higher form symmetries compared to zero form symmetry.
A quick question. So you the previous example you had this two form, right? That you were integrating over this surface.
That's right. Yeah.
And you had this hierarchy of perimeter, area, and so on. So when you go to even higher forms, so would there be, like you showed that the zero is related to a shift and all that, right? The zero term is, so will there be like a hierarchy of such shifts and so on for between, say?
That's a good question. I don't think so. I think you have the case where it will decay as the volume of the submanifolds, and then the other is decays as the enclosed, the volume enclosed. Yeah.
But can it sort of as a subsystem size? So for example, if I have L cube, can it sort of decay as L in that case? Is it possible?
I don't think so. Let me think. I don't think so. I think that's at least to my understanding, I think that's unlikely. Yeah. Yeah.
Okay.
Yeah. Sorry. Maybe, sorry. What I mean is actually, what I mean is, sorry, I said something wrong. So what I mean is that if it decays like that, you treat it as the same as the volume one, the sort of the one that decays with the submanifolds. It's still spontaneous symmetry breaking. Yeah, because in that case, you can always make it into a non-zero values.
Right. You can even exactly what I was asking. Is there like a hierarchy of the shift things that you can do? Right.
Yeah. So
by V to V, VR to V plus V naught kind of thing. So
yeah. The operator could have something like that. But then at the end, when we diagnose whether symmetry is spontaneously broken or not, we just compare it with the volumes of the submanifolds. Yeah.
Okay. Got it.
Yeah. Thanks.
And one question from the audience. You've identified two one-form symmetries, the magnetic and the electric one. So is the photon Goldstone boson of which of the two?
That's a good question. It's actually both. It's the Goldstone boson for both. And there's something subtle about that. This two one-form symmetry actually has what's called mixed anomalies. So that actually, in some sense, cut down the number of Goldstone bosons. So naturally, we thought, you should get two photons. But then because there's this thing's called mixed anomalies, hopefully I'll have time to get to. I realize I'm very slow. But that will actually reduce the number of Goldstone bosons. So that's why photon is both. Yeah. Good. Any more questions? Good. So if not, I think I only have 5 minutes. So I would like to get to 2 points and see just how much we can get to. So the first thing I want to discuss is one thing that's very, very different about one-form symmetries and zero-form symmetries, and that's in some sense make one-form symmetry very useful. It's about robustness of one-form symmetries. So a physical question we can ask is that, okay, photon is a Gaussian boson. Can we gap up photons? Okay. This is related to the questions that, in other words, we can state it as whether the one-form Gaussian boson is robust. So let's first review the case for zero-form symmetries. So a zero-form symmetry can be explicitly broken explicitly broken by local operators. Okay. So that means that if I find an emergent zero form symmetries, this requires fine-tuning. What do I mean by emergent zero form symmetries? What it means is that suppose I have some UV lattice systems that I have consider some generic Hamiltonians which doesn't have the symmetries that I impose. So this is for example what I consider here. So this is some lattice systems that I have some knob I can tune, okay, some couplings I can tune, and then I find that at some point it flows to a system that has suddenly has a G symmetries, G zero form symmetries that I didn't find before. Then we can ask what happens if I change this parameter a little bit, whether we can still find this G symmetry or not. But because the operators, because this zero form symmetry can be broken by local operators, so generically, if I tune some knob in the UV, it could induce some operators in the IR that breaks that is charged under the one form symmetry, that breaks the one form symmetries. So that means that generically, if I tune the knob in the UVs, I wouldn't find the zero form symmetries. So zero form symmetry is a very special things. Emergent zero form symmetry is a very special things. You only find it at very particular points. Okay, and related to this, so this means that zero form symmetry is not a robust notions. Emergent zero form symmetry is not a robust notions. And related to this point is that a Gaussian boson can actually be become massive if we break the symmetry, if the symmetry is broken explicitly, okay? So this is what happens to zero form symmetries, but now let's discuss what happens to higher form symmetries. So for higher form symmetry, I'll specifically consider a case which is one form and above, okay? I'll exclude zero form case. So one thing to notice is that because higher form symmetries doesn't act on local operators, so it cannot be broken explicitly by local operators. And this is remarkable because that means that if I find an emergent, let's say one form symmetries or higher form symmetries, then emergent one form symmetry is actually robust. What do I mean by emergent symmetry is robust? What I mean is, again, let's do the same things as before. We find that there's some special points that flows to a system that has enhanced emergent symmetries, okay? So what's nice is that now we can tune the knob again on the in the UV. But when we tune the knob, it was just induce some zero form, some local operators in the IR that change the Hamiltonian by some local operators. But because local operators doesn't break zero form symmetries, so that means that there's a finite regions around the neighborhood. There's a finite neighborhood around the point that I start with that will all flows to a systems that has an emergent p-form symmetries, okay, emergent higher form symmetries. And only if I tune to a point, so only if I tune past some kind of phase transitions, then I can make the symmetry disappears, okay? So this is very different from the case of zero form symmetries, that high form symmetries are robust. So if you find it, even if you break it a little bit, it will still reemerge in the UV in the IR. And this is actually a very important fact because this is related to a fact that I hope, I guess in Michael's lectures you might have already heard about, that in the case of toric code, which is a classic example of quantum hierarchical correction code, what it does is that it protects quantum informations in its one form symmetries. Okay. So because one form symmetries, even if you break it, it will still reemerge in the IR. So that means that that's why that's in a sense a more high level way to think about why toric codes can protect quantum informations, because this one form symmetries are robust. They can reemerge as the symmetries in the IR, unless you make a large enough deformations, to take you to a complete different phase. Okay, and related to this point is that Goldstone boson, Goldstone remains massless. For example, the photon remain massless for generic. If you find it emergent from some systems, then you'll find that they emerge you'll find that they remain masses under generic small perturbations to Hamiltonians. So that's why one-form symmetry is useful, because even if you don't find an exact one-form symmetries, as long as you find an emergent one-form symmetries, it's still good for many purposes. Okay, so I think I run out of my time. Maybe I can just stop here, and then we can take from next time. Yep.
Okay, thanks for that.
Okay, more questions.
So in the real world, considering we have electric matter, and I would expect that the electric two-form symmetry is explicitly broken. From this understanding, is it that the electric matter appears as a small perturbation? Is that how I think about it?
That's a very good question. And let me say that it's electric one-form symmetry. Just yeah, it's an electric one-form symmetry, not electric two-form symmetries. So that's a very good question. So this is actually the things I was hoping to get to. Maybe I can say a little bit about this. Just because you asked these questions, then I can get a little bit further away from what I said. So indeed, if you have some charge matters, dynamical matters, then you will violate the Gauss law, and so your Gauss law operators would not be topological anymore. So your one-form symmetry is explicitly broken. But now, because the matters is massive, so if you go to IR, this matters, you can ignore it. So the symmetry becomes topological again. So it re-emerge in IR. So yeah.
So sorry, if I understand you correctly, under renormalization, you assume that the mass is so large that they appear as probes whenever.
Exactly. That's right. That's right. That's right. Yeah.
More questions? I think your microphone is not switched.
Okay, so in the case of maxwell theory, you're saying that both magnetic one form and electric one form are broken. So that means tube loop and the Wilson loop, both of them have the perimeter law. Is this correct?
That's correct. That's correct. Yeah.
And then because the one form magnetic and one form electric anomaly, then that's why you only need one Goldstone boson.
That's right. Yeah. That's why you only have one photon. That's correct.
Because of the tube anomaly between the two one form symmetry, right?
That because the 12 anomalies, so these two symmetry generators actually don't commute, and that has a result of reducing the Goldstone boson. It's actually very similar to some mechanisms that discussing Haruki's paper with
I see.
yeah.
I see.
Yeah.
Thank you.
Yes.
More questions? There is one.
Could you explain again how you define the two lines, the logic behind that, when you're saying the conservation of flux?
Yeah, yes. So a 12 line is defined by what's called disorder operators. Is the way we define it is like how we define disorder operators. So what is a disorder operator? A disorder operator is an operator that cannot be written as a fundamental field from the fundamental fields, but you can write down a disorder operators by describing how the fundamental fields behave around these operators. So for example, in the case of Atoll lines, what we want is that we want that this is the operator where the field configurations become singular, right? So this is where the field this is line operators where it will emit non-trivial magnetic flux from this line operators. That this is like a source for magnetic flux. So that's how we define these operators. Let me just say another word is that there's another disorder operators that you might be familiar with. Is like, for example, in the case of Ising models, you can define some operators which are living at the endpoints of some Z2 symmetry lines. And then so the way to define this operators is that if you bring the order parameters around this operators, it has non-trivial holonomies. monodromies or holomies. Yeah, monodromies. Yeah. So in that sense, a top line is very similar to this disorder operators.
Okay. Yeah. One more question.
Hello. So I have a question regarding you explained that Wilson line picking up charge under this one form symmetry operation. You used Gauss law. Can you explain it a bit in detail?
Oh yeah, that's right. What I said is very simple. It's just let me see how to say this. So if I have a Wilson line sitting here, then if I look at equation of motion with respect to A, right? Then I'll get this things, but then I'll also get the term coming from the Wilson lines because the Wilson lines is made of A. So I'll get the terms that is proportional to delta functions. Okay. So if you look at this, if you rewrite it in components, it's nothing but the Gauss law that the divergence of the electric fields is given by the charge. So the Wilson line is like the probe charge. Yeah. That's good.
Are there more questions? Okay, if not, let's thank Hotat once more.
Thank you. Yeah. Yeah, I didn't get as far as I can, but
Okay.
yeah, tomorrow, yeah, hopefully we'll discuss.
On Monday,
That's right.
Okay.
On Monday, yeah.
Have a
Hopefully
nice
we can.
weekend.
Yeah. Thanks.